Hello, so in this lecture we will be covering the next three types of rules of differentiation. So from our last lecture, we have covered the first three types of rules of differentiation. First, differentiating the variable x with the order of power. And I said in this case I used the binomial theorem to prove this differentiation process. However, I said only for when n was an integer. However, when n is a real number, this process still applies the same. However, I said that the process requiring the proof requiring when n is a real number requires the utilization of logarithmic differentiation process. So after we learn the differentiation of logarithmic functions, I'll make sure to come back to that and resolve it, reprove it for you guys later. And the second was deriving a single variable of x. So this could be proved by using two types of ways, right? First, obviously, the equation of the first principal equation to manually find the derivative value of this variable of x, or you could use the first rule of differentiation when x has an order of power of 1, because x is just equal to x with the order of power of 1, right? So you could also use it using this method. And the third one was finding the derivative function of a constant function. And as you guys always know, when we inputted this constant value into the first principal equation, then you got the equation value of 0 over h, the h which was a value that is infinitely approaching 0, right? However, since h is not actually a 0 but a value that is infinitely getting closer to, it cannot be represented into a form of a 0. However, the numerator always has a 0. Numerator is absolutely a 0, thus making the first principal equation when you try to derive the constant exactly equal to 0. So basically, whenever you derive or find the derivative function of any type of constant, whether it is positive 0 or negative, then you're always going to get a derivative value of 0, consistent value of 0. And you could also prove this value by, drawing an actual manual function of a constant function, right? When we draw an x-axis and a y-axis here, and we draw any type of a constant function, I said the derivative function studies or delves into the correlation between the x and the instantaneous rate of change or instantaneous gradient at that corresponding x, right? So we're looking at the relationship between the x and the corresponding relationship of the instantaneous rate of change in the corresponding x, right? And you can see in this red constant function here, you can see that on any type of point of x that you put on, the corresponding y value, the corresponding instantaneous rate of change is always equal to 0, no matter what kind of values, what kind of x value that you input into this pink colored function. So therefore, whatever value, since every type of relationship between the x value that you choose and the corresponding instantaneous gradient is always equal to 0, then the derivative function, which is defined by a relationship between x and the corresponding instantaneous rate of change, it will always be equal to 0. This also applies that when the constant function is a negative value function, because derivative function looks as the relationship between x and the corresponding instantaneous rate of change of x applied on the function. So therefore, since we are only looking at the relationship between those two variables, despite the positive and the negative differences, the overall value of the derivative function will always be the same. Because no matter type of x value you choose, the corresponding y value will always have an instantaneous gradient of 0. So when you can see that there are visible changes when you actually draw a function geometrically, then rather than only using the equation of the first principle, you could also use various types of equations, such as applications of another law of derivatives, or just drawing it manually with the function, so you can visualize the relationship of the derivative function. So that's done with the review. So we will continue with our fourth rule of differentiation. So by actually showing you first, I said that there were 8 types of differentiation rules, right, that I've decided. However, today we will only be covering the 3, and these 3 will be when a function has been multiplied with a constant, and addition and subtraction of the functions, and multiplication of the functions. So those 3 types of new rules of differentiation we will be covering today. So our fourth rule, we'll be discussing about when a function has been multiplied with a constant. So therefore, let's say that a function looks like this. this is a type of function. So it's just any general type of function y fx. So this could be an exponential function, polynomial function, or anything. However, it has been multiplied by a constant, a common factor of a constant. And you want to define, you want to derive, you want to find the derivative function of this constant multiplied function of fx, right? So what do you want? What kind of the derivative value that you will get? What kind of general equation will you get? Well, I want to write this one more time here. The equation of the first principle. I said that this was the most important rule when you're solving the differentiation questions, right? And this importance also applies here, right? I said when you want to calculate the derivative function, then you would always have to input its function values into this limit equation of the first principle for you to get the value of the derivative function, y equals f prime x, right? So let's manually input this c fx into this limit equation here. What are you going to get? Well, if I input this equation, then hn, so fx plus h. So don't be confused here. Fx is the general function that you want to find the derivative function of. So this fx is not same with this fx. So this entire cfx will be the fx here, because this overall cfx is the function that we want to calculate the derivative function of. So when you input x plus h into this entire value, what are you going to get? You're going to get cf x plus h and minus fx. So fx, I said fx is the function that you want to find the derivative function of. So therefore, in this case, it's the entirety of cfx. So fx implies cfx. So you're going to subtract cfx. So if you are able to solve this equation, then the value that you get, the value that you derive from this equation will be your value of the derivative function. So let's casually evaluate this. So right from here, what do you see? You see the common factor of c in both of the variables, right? So you put the c out, you factor it out. Then c is a constant, right? So it has no relation to do with h and this limit equation. So it is allowed to be expelled out of the limit equation because the limit equation has no interest in c, which does not contribute to any of the included variables in the limit equation. So you're only going to be left out with c and the limit h approaches 0, h over f x plus h minus f x. So this is going to be the answer that you are left with. However, we have to solve this equation, right? However, when you look closely into this equation, what can you see? Compare this equation with this equation. Well, surprisingly, you get the same congruent equation. And since this equation is equal to f prime x, then I can also substitute this equation into f prime x. So ultimately, this is going to be equal to c f prime x, which will be the value of the derivative function of this function c f x. So when you derive a function that has been multiplied with a common constant, then what do you get? Well, you get a value of c f prime x, which if you interpret it or try to memorize it, the constant that you have multiplied with does not contribute to the differentiation process. It is never changed, it stays the same. However, the function that surrounds the constant, the function that has been multiplied with a common constant, will be the only factor that has been differentiated. So for example, when you're trying to derive a function of like 5x squared, then if you differentiate this, then since this is a function with a constant that has been multiplied, according to this fourth law that we just got the answer from, the constant that has been multiplied by the function does not take any part in the differentiation process. So you're going to be left with 5 comes through, and you're just going to have to differentiate this x squared, which if you apply the first law here, you're going to get 2x. And then it says that you have to multiply. You have to multiply, so therefore you're going to get 10x. Easy. So that's it with the fourth rule of differentiation. Yeah, fourth rule of differentiation. Now we're going to be going with the fifth rule of differentiation. So, I said that the today's three types of rules of differentiation that we're going to be learning is the one when the function has been multiplied with a constant, and when the addition and the subtraction of each function differentiation, and the multiplication, right? So we're going to be trying the addition and the subtraction function. So what does this kind of function look like in general? Well, the addition or subtraction type of function can be represented in this kind of format, where two kind of different functions are added with each other. Well, I'm just going to add minus here because we're going to be dealing with both of them, and both of them has a very, very analogous or similar types of characteristics. So now we want to differentiate them, right? So how are we going to differentiate them? Well, let's take a look. So of course, we're going to start off by inputting this entire function value into our first principal equation, because this is the only formula that we can find the derivative function from. Because like from these values, it was too obvious. We could draw any type of function and see the relationship, right? However, right now, this function can have infinites of different types of possibilities, enabling us to actually have a visual or any types of relationship that we can speculate or fathom this value of the derivative function from. So let's input this right into our limit equation here. This equation, because it is the most accurate equation that we can get. So again, this fx does not coincide with this fx here. I said that fx here is the entirety of the function that you want to calculate the derivative function from. So in this case, it will be this whole function here. So first, ignore the subtraction value here. I'm just going to try to find the derivative of the addition function. So let's say that the function that I want to calculate the derivative function from is just fx plus gx. So since it is fx plus h, because this is the entire function I want to find the derivative function from, I have to insert x plus h in both f and g, right? So it's going to be equal to f x plus h plus gx plus h, and then minus fx, so it's just going to be equal to fx plus gx. However, since there is a minus here, it's going to be fx minus gx, right? So now all I gotta do is having to evaluate this equation. Well, this kind of coincides with our last lecture of our complex limit equations, right? We wanted to tailor this form into an equation of the first principles. So let's try to do that again. Here, I can directly see the parts where I want to divide from, where I want to tailor it in form of a first principles. First, by looking at the factors, just fx plus h and minus fx, this is congruent to a form of the first principles here, right? And also, this equation and this equation, gx plus h minus gx. This is also equal to a form of the first principle equation. So, by keeping this in mind, by using just the rules of mathematics, I can separate these into two types of different fractions, because they share a common denominator. And this is not infringing the law of limits because I did not take consideration of the limits yet. So, let's factor this out into two types of different fractions, which is going to be equal to and then plus h gx plus h minus gx. So now what do I want to do? I've simplified the equation where you can directly see a kind of a direct form of the first principles, right? However, it cannot be interpreted as an exact first principle unless they are each given a limit identity like this one. So what do I want to do here then? I want to endow each of these fractions a limit identity. I want to put this limit symbol to each of these fractions so that both of them can simply be defined as the f prime x or g prime x, right? However, we have a condition here, right? We covered this on our complex limit equation, the third case pattern. For this limit, for us to endow separate limit identities to each of these two fractions inside the one big limit equation, we had a condition where each of these fractions, when applied with the limit, must have an existent value. So therefore, this means that this limit must exist and this limit must exist. So what does this imply? what does it mean that this has to exist? Then, just looking at this limit is exactly equal to f prime x, right? Because it is congruent exactly with this equation of the first principles. So, for me, if I want to give this and this a limit identity, then for this to exist, since this is equal to f prime x, it also has the same meaning that f prime x must exist. And also in this case, g prime x must exist. So for us to endow a separate limit identity to each of these fractions, we need a supposition that both f prime x and g prime x exist. Because if it doesn't, we are not going to be able to endow separate limit identities to each of these two fractions. Therefore, in that case, if f prime x and g prime x don't exist, or either of them don't exist, or if one of them don't exist, then this will not be able to be represented into a form of f prime x and g prime x. So we're just going to have to evaluate the limit equation in a separate type of way. However, on a supposition that both f prime x and g prime x exist, if we endow the limit identity to both of these fractions, then they will be represented into a form of f prime x plus g prime x. So you have to take a consideration here that the supposition was that both f prime x and g prime x existed. So in this case, so this is the differentiated value. So if I differentiate this, what am I going to get? F prime x plus g prime x. And if you were wondering about the subtraction part, since we are running out of time here, I'm just going to tell you the results. However, it's going to be the same technique that you use. Apply it to the rule of the first principles. And then if you input those equations and then thoroughly solve correctly, then you're going to get the similar type of value as the addition function. So when I differentiated the adding function, then I got the value of f prime x plus g prime x, right? However, when you actually subtract a function, then you're going to get the same value like this. However, it's going to be a subtraction. So basically, the plus and the plus remains the same, and the minus remains the same with each other. So if you start off with a plus, then you're going to end up with a plus. However, each side of the functions are differentiated, or derivative function, each derivative function. However, the symbol always stays the same. So since we're running out of time, I'm not going to prove it in front of here because I've already proved the first case with the addition type of functions, but I really appreciate it if you prove the subtraction type of function on your own, seeing that if you get the same results here of f prime x minus g prime x. And also, one thing in mind that there can be more types of functions. So for example, like I can write fx plus gx plus hx, or like wx or anything else. In that cases, I want to inform you that it's still going to be working out the same way. All you have to do is connect the symbol, don't change the symbols, and then just differentiate the functions. Just differentiate each type of functions as you go by, because that's going to be your final answer. And even if like we said that you want to calculate fx plus gx plus hx, well, you're still going to get the same answer, derivative answer of f prime x plus g prime x plus h prime x. Because all of the limit equations, as it gets longer, they each find a pair. They always get to find a pair. So they'll always be able to get the same answer. However, the derivative function of these addition or subtraction values will only differ because each of these functions, which were original functions, will be transformed into a differentiated version, and nothing else changes. So what types of examples of this fifth rule of differentiation can be applied? Well, looking at one of the examples, I'm pretty sure that we can think of 3x squared plus 2x, 3x cubed plus 2x squared plus 5. Let's say that I want to differentiate this function. Now what am I going to get? Well, if I differentiate this function, then I'm going to, this applies to the fifth rule generally, right? So I have to each differentiate this, 3x cubed, 2x squared, and 5 individually. And then the plus and the plus will remain the same. So let's go in by filling in our pluses. And then if I write down the differential value of 3x cubed, differentiate value of 2x squared and the differentiated value of 5, and that is going to be my final answer of the derivative function of this entire expression, right? So what happens if you differentiate 3x cubed? Well, we're going to use this fourth rule of differentiation here, right? We said that if a function has been multiplied by the constant, and the constant does not take part in the differentiation, constant remains the same. However, the latter part will be the only part that has been differentiated. So we leave the 3, and then we differentiate the latter x cubed and then multiply it by each other. So what happens when you differentiate x cubed? By using the first rule of differentiation, what are you going to get? 3x cubed. So multiply 3 by 3x cubed, you're going to get 9x cubed. No, 9x squared. So x cubed differentiated is 3x squared. My bad. And then, so the constant here, 2 also stays the same, and we're just going to have to differentiate x squared, which is going to be equal to 2x. So 2 multiplied by 2x is equal to 4x. And then the last 5 is a constant, right? So when you differentiate a constant, applying to the differentiation rule number 3, it's always equal to 0. But this is always going to be equal to 0. So this, when you differentiate this value here, you're going to get the derivative function of this value here. So simple enough. And since 0 is nothing, we can just simplify this as if it were nothing. And then, boom, this is your answer that it shows here. So even though this was a very easy type of question, or it only looks like the application of the fifth rule of differentiation, you can see that it requires the utilization of all these types of rules of differentiations. So therefore, it is crucial for you guys to always memorize all types of rules of differentiation that I've been discussing right now. Well, it does not always have to be memorizing the proof, but at least memorize it enough so that you're going to be able to fluently or flexibly apply those into the questions that you were given. Because these are going to be crucial for not only increasing your speed of solving, but also not making much mistakes as possible. Okay, so now we're going to be moving on to our sixth and our last rule of differentiation for today. And we will be covering the next two rules of differentiation in our next lecture. And I'm pretty sure that those are the big types of, really important types of rules of differentiation. But yeah, whatever. So our sixth rule of differentiation, the multiplication differentiation. Oh, and just a spoiler, if you want to listen, the seventh and the eighth one will be the chain rule and then the division differentiation. So what I said was the chain rule. Chain rule will be a little bit of notorious type of rule of differentiation that we'll have to learn, however. So that's why I moved it to our next lecture. So multiplication, what are we going to get? What type of function is it going to look like? Well, it's really simple, just like the word it implies. When two functions are multiplied by each other, what's going to happen if we differentiate these functions? Well, let's take a close look here. I have no idea how this function is going to be differentiated, so let's put it into our equation of the first principles. When you input it here, just normally like we have always done. So fx plus h. So since this is the fx here, this entire fx gx is the function that we want to calculate the derivative function of. Let's input x plus h in both of these equations. So we are going to get fx plus h, gx plus h, minus fx, which is just equal to this entire thing, minus fx gx. This is the equation that we have to solve, right? So how are we going to do this? What are we going to do? Well, surprisingly, I actually see nothing that I can actually convert any of these variables into a form of the first principles, right? But no need to be surprised here, because as we have always seen, we've covered these type of stages before. You remember the last lecture when we worked on the complex limit equations, also looking at back, referring to the pattern 3, if we did not have any variables that we could tailor into the form of the first principles, then what did we do? We artificially made those type of variables so that we could artificially transfer these equations into a form of first principle equations, right? So I'm going to do the same thing right now. Well, you don't have to know this. or if you want, you can try it on your own. So what kind of variables do you think that you have to artificially create? What variables do you think that you'll have to artificially create to actually enable to tailor this form of equations into a form of the first principles? Well, it's an obvious thing. This is kind of tough, right? Because you don't really know what kind of variables that you have to create. And just look at what I'm doing. If you could solve this, then that's great for you. But if you couldn't, well, of course, like there's nothing to worry about that. So I'm first going to subtract it. I want to subtract fx plus h gx. And then, since I subtracted something and I want no external overall change in this equation, I'm going to add it by fx plus h gx. Because of this, since these two are staying, however, with a different symbol, they can cancel each other out, leaving no overall external changes to this equation. So why did I do this? Well, you should first look at these factors. Don't you see anything? Well, by looking at the bright red colored circles, bright red colored two variables here, you're going to be able to see one type of a common factor, which is fx plus h. Both factors have fx plus h. And then when you look at the blue factor here, they also have a same type of common factor of gx. So what am I going to do? I'm going to separate these with variables which they contain the common factor with. So I have a feeling that since each of them have a different type of common factor, I should split them into two types of different fractions, because I believe that there is no connection between the red circle and the blue circle. So by doing that, what am I going to do? Separate these into two separate fractions. So working on the red circle first, I'm going to factor out the common numerator of fx plus h, and then the big numerator here, big bracket, gx plus h minus gx. Just follow through. And then we see plus h over common factor of gx for the blue circle. So gx, open up a big parentheses, and then fx plus h minus fx. Big closing parentheses here. So this is the equation that you get by rearranging equation from here. And what do you see? Well, we see that disregarding fx plus h, what do you see here? Well, we see the definition of the first principle, which can be converted into a factor of g prime x. And what about here? When you disregard the common factor of gx, and only by looking at this equation, this looks similar to equation of the first principle, which is equal to f prime x. However, then what do we want to do here? What do we generally want to do? Well, we want to endow separate limit identities to each of these equations, right? So what do we want to do? Well, we also need a supposition that both of these limits exist. When I insert limit equation to both of these fractions, both values of those limit equations must exist. And what kind of supposition do you need then? Not only the supposition that g prime x exists, but you also need a supposition that fx plus h when h approaches 0 also exists. So when these two existing values are multiplied with each other, their overall multiplied product will also exist, right? So, okay, so I get that. So g prime x must exist, but what does fx plus h approach to when h approaches 0? Just fx, right? So we need a supposition that for this value to exist, not only g prime x must exist, but fx must also exist, right? And what about this value here? Well, we also need a supposition that f prime x exists, but gx itself, we also need a supposition that gx exists. So based on the supposition that both four of those variables, or both four of those values, always have an existing value, then we are finally able to endow limit characteristics to each of these separate fractions. And what is this going to be equal to? Well, when x approaches fx plus h approaches, what does fx plus h approach when h approaches 0? Well, it's going to be approaching fx, and then what is this going to be approaching? When limit equation is given here, this is going to be approaching g prime x. Plus, gx is always going to be staying the same because it has no relationship with h, right? Just treat this like a constant. And then, what is this value going to be approaching? When we input the limit equation here, it's going to be equal to f prime x. And I just want to rearrange this equation by putting this one in front of this value. So, this is going to be equal to f prime x gx plus fx g prime x. So, this is going to be the value. F prime x gx plus fx g prime x. And I know that it is a very type of complicated equation, but the easy tip to remember is you can think that this is two types of different you can view this as two types of multiplied fractions added together. So it's like this. You first derive the first fraction, and then don't derive anything, just leave the second fraction and multiply them by together. And add the multiplied product of the fractions where you leave the first fraction alone, however, only differentiate the latter part of the fraction, and you multiply by them together. So, like this. Derive, no derive, multiply, plus non-derive, and then derive, and then add them together. So this is just a little tip to expedite or facilitate your memorization or understanding. And just one example that this type of questions can be applied to is, let's keep it pretty simple. Let's say 3x plus 2, and then 4x squared plus 7. If we actually did not have any information about this multiplication function differentiation rule, then our only way to solve this is by expanding this entire equation and then using these 5 types of rule of differentiation to solve. However, since we have this 6th rule of differentiation about the multiplied functions, we can use the 6th rule to solve this equation, right? So if we derive this, what are you going to get? Well, we use this rule. So we can deem these two parentheses, these different factors, 3x plus 2 as a function fx and 4x squared plus 7 as the latter function gx, right? So I first said when you were deriving the multiplied function, you first derive, non-derive, multiply, plus non-derive, derive, right? So let's first derive this function, which is just going to be equal to 3. And then I leave this latter part alone, which is going to give me 4x squared plus 7. And then I add them, and then I do not derive the first part, fx. However, this time derive the second part of the latter function, which is going to give me just multiplied by 8x. So when you evaluate this equation, then this is going to be the value of the derivative function when you differentiate this multiplied fraction values. So you can definitely see here that these types of rule of differentiation definitely expedites and facilitates your speed of solving and also mitigates the chances that you'll make mistakes, because not only that you're actually manually computing those equations by plugging individual functions into the first principal equation, but you're actually using the general formula of rules of differentiation. So as long as you absolutely memorize these concepts really rigorously and strictly, there's gonna be no way that you will be making mistakes on your future problems. And from our next lecture, we'll be covering the last 2 types of rules of differentiation on generic types of functions. The seventh, the chain rule, and then the eighth, the division function processes. So, by able to utilize all 8 rules properly, there will be no types of functions that you won't be able to differentiate, I promise. So, thank you for listening, and I'll see you on our next lecture. Thank you.